Hello everyone, my name is Jack Jorgensen. I'm a PhD student in the Department of Mechanical Engineering at the University of Western Australia in Perth. I'll be presenting today our paper entitled Predicting Bolt Stress Under Uncertainty in Offshore Wind Turbine Structural Connections using a Gaussian Process Surrogate Model. I'll provide some background on offshore wind structural connections, an introduction to the Gaussian Process Surrogate Model approach, an introduction to the case study examined, diving into results, presenting findings, limitations, and future work. I'll then close out with an outlook on next steps. Firstly, some motivating background information regarding offshore wind. The Global Wind Energy Council projects installed capacity to more than triple to 2025. Further, offshore wind is significantly affected by the cost of operation and maintenance activities, on the order of 25 to 30% of overall energy cost. It's then reasonable to suggest that any action that can reduce uncertainty in life analysis for offshore wind turbine structures can provide a tangible benefit in optimizing inspections, reducing offshore work costs, and reducing technician safety exposure. In this paper, we are interested in the opportunities in fatigue life assessment of the structure and managing uncertainty in fatigue. We are particularly interested in the fatigue assessment of bolted ring-flange connections in the offshore wind turbine structure. On the left, a basic breakdown of some locations in the structure where major bolted ring-flange connections are located. Increasingly, the connection between the monopile foundation and transition piece, see on the right, is being made with bolted ring-flanges. See Melinda's paper from 2020 for context on this uptake. One of the primary concerns when designing the overall offshore wind turbine structure is fatigue lifetime. Schaumann and co-authors in their 2018 paper suggest more than 1 billion load cycles are possible. Literature in the space also records flange alignment, see again the paper from Schaumann and co-authors from 2018, and bolt preload, see Brathwaite and co-authors from 2020, as significant considerations in fatigue design. A common approach for bolted ring flange design is to assess a segment model, as shown on the left, analysing the segment aligned with maximum tower shell load Fz. The transfer of Fz to bolt load is of particular interest. Schmidt and Newper introduced an analytical method to represent this load transfer function in their paper from 1997, referenced in DNVGL design standard ST0126 for turbine support structures. This method is efficient, however does not treat bolt bending, does not model stress hotspots, and only bounds flange imperfection tolerances. ST0126 also permits the use of structural finite element simulations to simulate load transfer. FEM simulations are likely more accurate than the analytical method, however will be much more computationally expensive. When considering fatigue design, the choice of analysis technique can influence the calculated fatigue damage significantly. Schaumann and Eckstad in 2015 and Madsen and co-authors in 2017, amongst others, have shown divergence of calculated fatigue damage between the analytical and numerical approaches. Further, to assess uncertainty of fatigue damage against uncertain inputs, a Monte Carlo simulation approach is required. Schaumann, Eckstad, and Stang performed an MC simulation in their 2018 paper, requiring a significant number of analyses for differing inputs. This may be possible, though likely inaccurate, with analytical methods, but it is prohibitive for FEM simulations. It is here, in the current gap between computational efficiency and accuracy for analytical and numerical methods, that a surrogate model approach may offer value. The approach of surrogate modeling emulates the complex input-output relationship of simulation models through some mathematical technique. One such approach is to utilize the Gaussian Process Surrogate Model. Here, we assume the mapping of the FEM simulation input to FEM outputs, the bolt stress field, can be represented with an unknown and smooth and continuous function f. We can use the information provided in the observations of f at x, alongside some assumptions about the form of f, to predict the value of the function f at x star, some other set of input points on the input space. We assume the function values f are drawn from a Gaussian process prior, such that any subset of realizations are distributed normally. A Gaussian process is an infinite dimensional multivariate Gaussian distribution over a function space, any finite subset of which is also Gaussian. The GP prior, essentially a prior assumption on function form, is represented through a mean function and covariance kernel, discussed later. The manipulation of multivariate normal distributions is well understood, and as such the prior can be conditioned on the observed data f of x relatively easily. This results in a posterior predictive distribution, p of f star, given f, x, and x star, where we can predict the value of f of x star alongside some uncertainty bounds. Using the GP surrogate model avoids the need to continually query the computationally expensive FEM simulation at different points on the input space. We move to the case study considered in the paper. The bolted ring flange is based on an application detailed by Madsen and colleagues in their 2017 paper. A 6 meter diameter connection with 140 M64 grade 10.9 bolts is modelled. The flange face material is assumed to be S355 ml structural steel. 6 locations of interest are assessed, locations A to F. GP surrogate models are built to predict the stress field at each location. The flange arrangement is modelled in the SimScale FEM package as a static, nonlinear simulation of the segment model of the maximally loaded segment with a simplified bolt nut geometry. Tetrahedral meshing is used, and the stress field under assumed loading Fz and boundary conditions is simulated numerically. Contact is modelled between flange faces. We consider bolt preload and tower shell load as the dimensions of the input space for the FEM simulation. We use a Latin hypercube sampling technique to randomly select a discrete number of points to provide the design space, maximizing coverage on all input space dimensions. We randomly divide the design space into training points, can be thought of as the matrix X from our GP definition earlier, and validation points, X star. Later, we examine the influence of relative size of the training and validation sets on predictive accuracy. The figure at left shows the design space selected, training points in blue and validation points in orange. We run our FEM simulation at each design space point, generating results on which we wish to train the GP surrogate model. To implement the GP surrogate model, given FEM simulation results, we select a mean function and covariance kernel. The mean function describes any global trend of the unknown function. We select a zero mean function for the paper. A covariance kernel represents variation of the unknown function value at different inputs x and x star. We utilize the squared exponential kernel. This kernel is shown in the bottom center. See the paper for further discussion. Given the observed data, we use well understood conditioning results and the maximum a posteriori or MAP method to estimate the hyperparameters. We use the GP Flow Python module to construct and train our GP surrogate model. We then validate and perform diagnostics of predicted performance for the GP surrogate model. Once we are satisfied that the GP surrogate model provides reasonable predicted performance, we can apply it to predict accumulated fatigue damage, comparing it to the baseline FEM simulation. This fatigue case is based on a synthetic load profile. We generate this load profile by considering the work of Schaumann and co-authors from 2018 and scaling it to our case study. The authors assumed a tower shell load profile with a tower shell load cycle mid-load, Fz mid, and load range, delta Z, are drawn from normal and exponential distributions respectively. We then use the 3 different methods of load transfer analysis, plus an assumed bolt preload, to predict bolt load cycles. These bolt load cycles are referenced to the bolt tensile stress area and binned into stress range blocks. Selecting an appropriate SN curve from the Eurocode 3 reference standard, we can assess the accumulated fatigue damage of these stress range blocks. We compare the predicted damage from the Schmidt-Neuper, FEM and GP surrogate methods and the computational costs to judge the value of using a GP surrogate for this task. All results are shown based on a training set size of 39, validation set size of 20, a total of 59 points for the design space. We first inspect a comparison of von Mises bolt stress prediction at location C from the FEM simulation baseline with red circle markers and approximated by the GP surrogate model black crosses. By inspection, the predictive accuracy of the GP surrogate model appears reasonable. The general form of the GP surrogate model prediction follows the FEM simulation baseline, with globally increasing bolt stress against both dimensions. The GP surrogate model seems to predict the changing regime of bolt stress against tower shell load relatively well. You can see this change from around 1000 kilonewtons onwards. We observe relative prediction errors above 0.5% at higher tower shell loads. In general, prediction errors are below 0.5%. These errors are considered sufficiently low since fatigue assessment is performed on bin data, where bin width is larger than 1% of full-scale load. We look to the paper by Bastos and O'Hagan from 2009 for Diagnostic Techniques. We first check the sensitivity of the prediction results against the size of the training set. At left, we observe the RMS error and average variance of the validation point predictions converge above 35 training points. Therefore, we utilize 39 training points as the basis for GP prediction. At right, we observe the 95% prediction intervals of the GP surrogate model. Most prediction intervals intersect the diagonal, denoting the baseline FEM results, with all close to the diagonal. Some wider predictive intervals are observed at some validation points. These are discussed further in the paper. Whilst the GP predictions may be improved by increasing training points in certain regions of the input space and providing a non-zero mean function, performance for our purposes on fatigue prediction is considered suitable. The table presented here summarizes some metrics for the training and validation computation time of the GP surrogate model compared to the runtime of the FEM simulations. Computational runtime metrics are provided in seconds of wall time and assume no parallel computation. The GP surrogate model shows a potential speed up of 16,000 times over the FEM simulations for fatigue lifetime assessment. See the paper for further detail. We then apply the GP surrogate model to predict fatigue damage, given the synthetic tower shell load profile described previously. The histogram plots compare the bin stress ranges of generated bolt load using the Schmidt-Neuper method, red on the far left, the GP surrogate model, blue, center, and the FEM simulation, green, right. We observe, as per our expectation, that the Schmidt-Neuper method is more conservative, predicting higher counts of larger bolt load ranges. The predicted fatigue damage is shown in the table at the bottom. The Schmidt-Neuper method is very conservative as compared to the FEM simulation. Further, we note the prediction using the GP surrogate model provides a good approximation of FEM results. This result suggests the GP surrogate may be a useful tool in predicting fatigue damage. Uncertainty bounds on the fatigue damage predicted by the GP surrogate model are shown. These are calculated considering the worst case combination of predictive variance when using the GP surrogate. These bounds are quite wide and reflect both the bounding method used and potentially the variance in GP prediction discussed previously. Through the efficient computation of the GP surrogate model, we now also have an accessible method of querying the uncertainty of the damage prediction in response to variation on the input space. This may be utilized in a full Monte Carlo simulation to assess fatigue damage uncertainty against assumed distributions of input parameters. Here we investigate a simple example, varying the bolt preload from the starting assumption with a relaxation factor of 0.9. Shown in the plot is the damage contribution of each stress range block. The baseline for FR equals 0.9 is shown with circle markers, bounded by the uncertainty region to FR equals 0.8 inverted triangles and FR equal to 1 triangle markers. We expect a lower preload would lead to increased fatigue damage, and this is observed in the plot. Achieving such bounding through the use of FEM simulation model would be onerous. The predictive uncertainty identified when discussing results may be addressed through increased training and consideration of appropriate mean functions. Methods exist to extend the GP surrogate model to a multi-output GP. This would mean simultaneous prediction of stress results at all 6 locations of interest. To the extreme, there may be interest in extending prediction across the full geometry, but this may not offer computational advantage. We note the opportunity to pursue higher fidelity FEM simulations, where, for example, the bolt and nut thread modeling could be included, full contact models could be implemented, and flange imperfections could also be implemented. This enhanced detail offers the opportunity to explore direct damage propagation methods, such as those studied by Logan and Somonov for stress concentration at bolt threads using a GP. Further, incorporating flange imperfections could mean expanding the GP input space dimensions. Our results have shown the promise of the GP surrogate model approach to predicting bolt stress in bolted ring flanges in offshore wind turbine structures. This is a good start, and the future work identified could extend usability. We are looking forward in the long term to real-time fatigue damage state prediction for these bolted ring flange connections. More direct methods of damage propagation may be possible for an operational context. I'd like to extend an invitation to any listener who may be interested in this work to get in touch with me at the email address shown in the paper. I'm particularly interested in hearing industrial views on this work and would welcome feedback. A list of references and acknowledgements for this presentation is shown. The paper provides the full set of references. I'd like to take this opportunity to acknowledge the support of the Offshore Hub and open the floor to questions.